understanding the critical disruption of the Atlantic conveyor belt. The rapid weakening of the Atlantic meridional overturning circulation represents an existential climate threat that acts as a primary catalyst for global environmental destabilization. As we navigate the complexities of 2026, the scientific consensus regarding our oceans has shifted from theoretical modeling to observing tangible, alarming physical changes in deepwater currents. This circulation system, often visualized as a massive oceanic conveyor belt, performs the essential task of transporting heat from the tropical regions toward the North Atlantic. When this process falters, the resulting thermal imbalance disrupts the delicate climate architecture that has supported human civilization for millennia. The engine driving this circulation relies on the density of seawater. As saltier, colder water sinks in the North Atlantic, it pulls warmer surface water from the south. Today, we are witnessing a massive influx of fresh water derived from the accelerated melting of Arctic glaciers and Greenland's ice sheets. This fresh water is significantly less dense than the saline water naturally found in the North Atlantic. Consequently, the water fails to sink with its usual force, effectively clogging the circulatory pump. This physical reality underscores the intimate connection between terrestrial ice loss and the deep ocean dynamics that regulate our global thermostat. Quantifying the acceleration of oceanographic decline. Scientific assessments indicate that we are entering a phase of profound historical change regarding oceanic health. The data collected by researchers suggests that we are witnessing the most significant slowdown of these currents in over a millennium. By analyzing sediment cores and historical climate proxies, oceanographers have confirmed that the currents are not merely fluctuating due to natural variability, but are responding directly to human-induced thermal forcing. The following points outline the specific structural shifts currently being observed. Projected kinetic decay. Current models suggest that the AMOC could suffer a reduction in strength exceeding 50% before the turn of the century in 2100. Such a decline would push the circulation into a state of instability that has not been witnessed since the end of the last glacial period. Thermal inversion zones. The development of a persistent cold blob south of Greenland serves as a physical indicator of system failure. Because the northward transport of heat is stalling, the region is cooling even as global average temperatures rise, creating a localized anomaly that disrupts regional pressure gradients. Dynamic sea level feedback. The redistribution of water mass due to the weakening current is forcing an abnormal accumulation of water along the eastern coastline of North America, accelerating regional sea to level rise beyond what is seen in global averages. Assessing the consequences of climatic whiplash. The consequences of an AMOC collapse extend far beyond the cooling of individual regions. We must understand these events as a series of interconnected feedback loops that result in weather whiplash, where climate systems oscillate between extremes with little warning. The transition, should it reach a tipping point, would not happen over centuries, but rather over the course of a single decade. This compressed timeline leaves ecosystems, agricultural zones, and urban infrastructure with minimal time to adapt to the profound shift in local weather patterns. The ramifications of this change are distributed unevenly across the globe, yet they remain universally impactful. Consider the following projections regarding the potential fallout of a collapsed circulation. European thermal shift. A reduction in heat transport could trigger a drop in European surface temperatures of approximately 10 degrees Celsius. This would fundamentally alter agricultural viability, requiring a total overhaul of food production strategies across the continent. Coastal inundation. The disruption of the current prevents the normal flow of water away from the North American coasts. This phenomenon can result in an additional 2 feet of localized sea to level rise, threatening major metropolitan hubs with frequent catastrophic flooding and long-term coastal erosion. Global hydrological disruption. The cooling of the North Atlantic creates a mismatch in the intertropical convergence zone, which is responsible for seasonal rainfall. Shifts in this zone are expected to trigger prolonged multi-year droughts across the Sahel, parts of South America, and extensive regions of Asia, placing millions of people at risk of water and food insecurity. The necessity of adaptive climate literacy. As we evaluate these findings in the context of our current date in 2026, it is vital to approach the data with both critical rigor and a sense of objective urgency. The AMOC is not a distant concern. It is a current active component of the global climate system that is undergoing measurable structural degradation. Developing a comprehensive understanding of this mechanism allows for better preparation, as it highlights the necessity of localized infrastructure resilience and global policy shifts aimed at curbing the root causes of glacial melt. Furthermore, these shifts emphasize that our planet operates as a singular unified machine. Changes occurring in the high-latitude Arctic do not remain confined to the poles. They travel through the medium of the ocean to touch every continent. Recognizing that the stability of our weather, our coastline, and our agricultural productivity is contingent upon the fluid dynamics of the North Atlantic is essential for any modern approach to environmental stewardship. We must remain vigilant, prioritize the ongoing monitoring of these oceanic currents, and support the scientific endeavors that allow us to track these changes with increasing precision. In conclusion, the weakening of the AMOC represents a critical transition in the Earth's climate systems, characterized by a rapid slowdown of heat distribution and a subsequent cascade of extreme weather events. The physical evidence of a cold blob, the potential for severe European temperature drops, and the threat of increased sea level rise on the U.S. East Coast underscore the urgency of the situation. By acknowledging these risks and focusing on the interconnected nature of our global environment, we are better equipped to comprehend the necessity of systemic change and the importance of scientific monitoring in protecting the stability of our future world.